So by way of introduction, let me take you through what I want to talk about today. And of course, we'll leave time for questions at the end so we can get to any specific questions that you have about teaching introductory stats with JMP. Now, first, who is this webinar for? And so I'm presuming that you have some previous experience teaching statistics. Now, it's okay if you don't. If this is your first time teaching a stats course, that's actually great. It's nice to see these kinds of overviews before you do it the first time. But most of what I'll talk about today is how you might incorporate JMP into an existing statistics course. And so I'm taking it from that approach. Now, I'm also assuming that you might have some experience with JMP already, or at least have seen some of our other webinars this season. And now the reason I'm hoping you've seen JMP before is JMP, of course, can do a great number of things. And what I'll be talking about specifically today are those features or aspects of JMP that I think are most useful for teaching introductory statistics. Now, if you don't have any experience with JMP, that's actually okay as well. In the first section, I'm going to talk a little bit about JMP in general and point out some of its utility for all sorts of things. But I am hoping you've seen a little bit of our JMP webinars, or at least have used JMP before. Now, I'm hoping that you're open to using software and teaching statistics. It's also okay if you're not, if you're just here to see how it might look. I'll say the first time that I taught stats, I taught it very traditionally. I didn't use software at all. I used hand calculations and thought that was the best way for my students. As I started to use software myself a lot more, I found that it brings a lot of value to the course and didn't do some of the things I worried about, like detracting from the teaching of statistics. In fact, I found that using software actually enabled me to teach statistics in a much more comprehensive and powerful way. And so I'm hoping that you're open to that. And if you're not, hopefully you'll at least listen to some of the things we have to say and maybe see some value in using software. Now, I'm expecting you'll be teaching an introductory statistics course at some point soon. It's okay here if you're just kind of looking to see what you might do. But I'm thinking about this webinar as a way to prepare you, or at least give you some of the resources so that you might prepare that class using software. And it's actually okay that you use software for both small and large classes alike. I've taught classes with JMP, when I've had 30 people in a course and classes where I've had 300. There are different approaches, and I'll point some of those out. But certainly statistics can be taught with software, whether your course is large or small. Now, just to sort of talk about statistics teaching in general, I hope you've seen the GAZE guidelines for the teaching of statistics. These are guidelines for the assessment and instruction in statistics education. And you could find this just by searching the GAZE report online. And GAZE, these instructors and professors just released a new report in 2016. And just to summarize quickly for you, the GAZE report's all about suggestions for how one might teach an introductory or even intermediate statistics course. And so they're really general purpose guidelines and things to keep in mind. And I think they're a wonderful context to talk about what we'll talk about today. So teaching statistical thinking is, of course, one of the main ideas. Focusing on conceptual understanding, making sure that students leave your course understanding the why about statistics, not just the how. Integrating real data with a context and purpose. This is critical, making sure that data analysis isn't done in sort of a vacuum. All data analysis is about solving questions or answering questions. And so giving students real data and having a real question to answer is a powerful way to teach statistics. Certainly fostering active learning. Passive learners don't retain. So making sure students take an active role in their learning. Using technologies to explore concepts and analyze data, that's something we're going to talk a lot today about. And using assessments that improve and evaluate student learning. So assessments that aren't just there, formative assessments, not just to assess what they've learned, but hopefully give them some training and some experience. And so that's going to be somewhat of the context for today's webinar. Okay, as for what we're going to talk about before I get into what JMP is, I'm going to give you a little bit of an introduction to just JMP overall if you've never seen it before, or if you've seen it before but maybe haven't seen it recently. We're going to spend a bit of time talking about how we might teach statistical concepts using software, specifically how we might do it in JMP. And this is going to be critical because concepts form the foundation for the why of statistics. All statistical procedures revolve around some core sets of concepts that if students grasp, they'll do great in later courses or even just as consumers of statistics in their everyday lives. We're going to spend a little bit of time on how we might teach statistical practice within JMP. That is how we might teach data analysis and teach good practices when it comes to understanding and evaluating data. We'll look at some testing and evaluation, so some tips I have for how we might assess what students have learned, both in terms of concepts, but also in terms of JMP. If you're using software in a course, you want to make sure that students come out of it learning how to actually do these analyses. So I'll spend some time with that. I'll give you some tips for how we might use software in class. From the many years I've spent teaching, some things I've learned about how to get students to really be involved and engaged with their analyses in class. And then how students can get JMP. JMP's very affordable for students, and we have several ways to do that. And then finally, I'll end with some resources to remember. And actually, you're looking at one of them on the left-hand side right now. And this is our academic landing page at jump.com/academic. And so if there's one URL you remember today, remember that one, jump.com/academic. Because here we have a lot of resources, and many of the things I'll mention today you can find here as well. So how to get JMP, the page on sort of licensing and how students can get access to it, ways to learn JMP, and so that'll take you to the bottom section where we have a really big collection of resources that really get you started. So, one-page guides, short videos, all these things that you can incorporate into your course and make it easy to really incorporate software. And finally, the academic webinar library, so where the recording of this webinar will be. All right, so let's close out of Chrome here, and actually let's start within JMP. I'm using a JMP journal on the right, and I'll mention this actually under tips for in-class use. JMP journals are a great way to organize content you're going to show. Obviously, I'm using it for this presentation, but they're also great ways to organize your output and to sort of collect things from JMP. And so let's actually step through what JMP even is if you've never seen it before. And so JMP is actually a family of products. They're Mac and PC versions of software for data analysis. JMP Now is JMP, JMP Pro, JMP Clinical, JMP Genomics, and even a JMP Graph Builder for iPad. And so it's a really large collection of different professional data analysis pieces of software. And JMP started about, 28 years ago now, so 1989 by John Saul, one of the co-founders of SAS. And his idea was to make software that was visual, interactive, and powerful, to make data analysis easy, but to enable scientists and engineers, principally, to get a lot of value from their data. And I'll just pull open some sample data. If you've never seen what JMP looks like, it starts off with the idea of having a data table, rows and columns with our data. These happen to be measurements on different flowers, so different irises. These are actually from Ronald Fisher. And the idea with JMP was to make data analysis seamless. That is, you can ask a question, get an answer. You don't have to write code, but you get to visually explore your data. And so I'll go to a platform in JMP, distribution. The distribution is all about looking at univariate output. So distributions and looking at histograms, that kind of thing. Notice JMP is very quick. We didn't have to write any code to get to our histograms. We get summary statistics for the numeric columns, and we get frequencies for the categorical columns. But JMP was built at a time where statistical software could be interactive. So if I select the lowest petal length flowers, those observations are highlighted in the table. They're also highlighted in every other graph. So I can click between the different species and see those observations in different distributions. So JMP works differently than other software. It's interactive, it's visual, and it lets us explore our data by clicking and dragging. I'll go to another representation of these data. Let's go to Graph Builder, and I'll look at just a bivariate relationship. I'll drag two of these variables in. Let's actually put species as an overlay, and let's put on some little density contours. So now we can see where these flowers are in bivariate space. And again, because of the interactivity, I can grab those flowers that are sort of indistinguishable in bivariate space there between the two here. So we can see it's the versicolors and virginicas. So being able to explore your data set, being able to drag and click through things makes it powerful for students and makes it enjoyable. One thing I love about JMP is just showing students that, data exploration can be fun, it can be easy, and still they're learning a tool that's used by professionals, professional scientists and engineers at major companies. And so they're going to be learning something that's fun for them, but they can also put on their resumes, once they complete the course. And so that's the idea of JMP, is to make data analysis simple and straightforward, but to enable you to do quite a bit with just your mouse and keyboard. And of course, it's very extendable. For students who go on into advanced courses, they can connect it to Python or connect it to R. They can write code. You can write applications within JMP. So it's software that's going to grow with them too. So they're not limited by the software, even though it is very friendly. All right, so going back though, if we're thinking about JMP in a course, we're going to want to teach a number of different things using JMP. And maybe the first is going to be statistical concepts, the standard curriculum for an introductory course. We need to get through some really basic core concepts before we get into hypothesis testing, before we get into, doing regressions. And some of those core statistical concepts are really made more easy to understand using JMP software. And so we've done a little bit of work putting together some modules and teaching demonstrations that make it easy to discuss these concepts. And I want to show you a resource within JMP. It's under the Sample Data Library. And so under your Help menu, Sample Data, and there's a section here, and I'll just mention, if you haven't seen the sample data in JMP, we have a lot of real data here, almost 500 data sets, all organized by type of analysis they're good for. And so if you're teaching, let's say just graphing, and you want to pull open, here I'll pull up some US or world demographics. The world demographics are great. And so if you're teaching, data visualization and you want to talk about looking at world demographics, these data are built in. So you can go right to Graph Builder, drag territory to the map shape, and, let's look at 5-year mortality rates across the world. So the real data being in here makes it really powerful and fun for students to explore. Right, so the sample data is worth looking at, but what I want to talk about at this point are the teaching concepts. And so this is under the teaching resources section right here. And if you look under the teaching scripts section, we have a couple of different categories. So the interactive teaching modules and these teaching demonstrations. And all of these are little applications built in JMP that allow you to demonstrate core concepts within statistics. And I'm going to start first by talking about the teaching modules. So these interactive teaching modules here. Now, if you're using a version of JMP earlier than version 11, you can get the interactive teaching modules at jmp.com/tools. But these are all available right inside the software with version 12 or higher. And so once you're in the interactive teaching modules section, each of these is really a full-fledged module or teaching demonstration to teach a particular concept. And the ones I want to talk about, I've sort of pulled out to the right-hand side here, because what I want to show you is a little bit in depth on how these work and maybe a couple suggestions on how you might want to incorporate them within your curriculum. Now, the first teaching module, the distribution calculator, isn't one so much for teaching a concept, but one to make the probability calculations that a lot of us use in our courses a little more visual and a little more interactive. When I first started teaching statistics, I used a lot of tables in the back of my textbooks. But as I started to use JMP more, I love this distribution and probability calculator, since for all these different distributions, students can enter in their values and not only read out the probabilities, so the proportion of the distributions, but they can get a sense of what that even relates to by looking at the graphics. So for instance, if I want to look at the proportion of a normal distribution greater than some value, let's say greater than 1.96, I enter that in and I can read off really easily 0.025. And I can also see within the plot where that portion of the distribution is. And that makes it really nice and really sort of compelling for students to understand what is going on. And it also means that instead of having to work from a unit normal distribution, mean of 0 and a standard deviation of 1, students can start off with a distribution that has some parameters that relate to them. So let's say we're working with a typical IQ distribution, a mean of 100 and a standard deviation of 15. We can ask a question, what portion of the population has a value for their IQ greater than, let's say, 125? And that portion of the distribution is now shaded. The probability can be read off, and these probability questions can be answered, but they can also be visualized very easy. One thing I was told students was, when doing these lookups from a table, always draw your distribution and shade the portion of the distribution you're trying to find. Now, this does that for them. It assists within this question and answer process such that they get very quickly to an answer, but they also don't have to, read through a table to find a value, because that gives a kind of a false impression within how statistics is done. We don't use lookup tables, we use software. So the distribution calculator is a great way of working through these basic questions and problems. And it supports a large number of distributions, so ones that I typically wouldn't use in an intro class. But certainly the normal, the t, chi-square, and f are all here. And as we work through hypothesis testing logic, this distribution calculator ends up being quite useful for them to see, how these different distributions look and how they react. Right, so that's the distribution calculator for real basic stuff. Now, the next module I want to talk about certainly relates to something we all talk about within basic or introductory stats, which is sampling distributions of the mean, certainly forming the basis for all of hypothesis testing. How does the mean respond when we take samples from some population? And the way this sampling demo works is, and you'll see this in most of the interactive teaching modules, we have population characteristics along the side. So setting up some distribution in the population with some particular shape. We have characteristics of the demo. So how many samples we want to take when we click a button. So as I draw additional sample, how many do I want to take? And what is the size of each sample I take? And then some additional tools, and I'll show you what these do in just a second. But let's set this up as a simple situation. So we have a variable we can call whatever we want. Height's fine. Let's say the population mean is set at 60, and the standard deviation is 5. You'll see the distribution of the population data here. And so presuming that this is maybe some population we're drawing and we're measuring their heights. Now let's leave the demo characteristics as one sample, but I'm going to set the sample size here to a size of 3. So every time I click draw, 3 individuals are drawn and shown in the distribution of sample data here. And in the distribution of sample means, the mean is taken for heights of those individuals and plotted right below. So what we have is every time we draw, we're plotting the mean for each sample. And what I like about this is, especially when first teaching students the idea of a sampling distribution, you can go about it slowly through drawing these samples, each one showing what the mean is and how that mean is plotted down below. So for every single sample, showing how that connection is made. And making it manifest is really important. These large sample or sort of approximations to distributional theory, that can get somewhat abstract for students, unless they see each sample being drawn and put into that distribution of sample means. Now, once they get that concept, I would say after doing this 10 or 15 times, say, okay, well, we're going to add, let's say, 1,000 samples at once. So draw those samples. And once you do that, you can show that distribution of sample means. And from here, certainly you can ask questions. What is the probability of drawing a sample with a mean above, let's say, 65? And those questions can actually be answered empirically. If we like, we can make a data table from those samples. I'll click Make Data Table here. And notice that every sample mean we drew from the 4,029, because I clicked, draw additional samples multiple times, every one of those samples is shown in this table. And using basic or core features of JMP, for instance, distribution, I can actually look at the distribution of those sample means, and I can select. I can say, oh, grab me those observations that were actually larger than a certain value, 170 here out of 4,029, so we can do the calculations. Now, to make it simple on ourselves, what I typically will do is say reset samples and just draw, let's say, 10,000 samples all at once. So draw those samples, make a table, and now out of the 10,000, we can work on certain sort of probability questions. So again, going to the distribution platform, looking at the sample means, and now we can, grab observations that are all greater than a certain value. Now, if you've never seen JMP before, there are some tools that make it very easy to do this sort of selection, and it's under the rows menu, the data filter. And one thing I love about the data filter is it's going to ask me which column do we wish to filter on, and so I'll say sample mean, and I can say just show me the means that are, let's say, 65 or larger, and so I'll type in 65 here. It selects them. It says 410 matching rows. And notice that they get highlighted in the table as well. And so we can look up that proportion of this empirical sampling distribution. And then remember, since we have the distribution calculator, you can ask students to compare it. What distribution reflects that real empirical sampling distribution probability? And very quickly, they're going to find out that it's the normal. That's why we have a normal approximation for sampling distributions under a large number of conditions. Right, so working with this empirically, we get students to form that connection to how a sampling distribution works and what it means. Now, you might already be guessing that this doesn't just give us an ability to discuss standard error or how sampling works and how the mean has error in estimation, that population parameter of mu, but it also gives us an ability to demonstrate probably one of the most fascinating and wonderful characteristics of sort of distributional theory, the central limit theorem. And so if we start off with a population that isn't normal, let's say it's skewed right, so there's this heavily skewed distribution, or even a uniform population, or even a population you give JMP here, you can actually feed it your own data. Let me start off with a skewed right distribution. And if we have sample size still at sample sizes of 3, once I click draw, and I love for students to see this, once they've seen that nice normal shape from the first draw, now they see this, and this doesn't look very nice and normal at all. It's got a skew. So this is our distribution of sample means, but is now actually skewed. And if they make a table and they go through and look at the distribution of that, the sample mean, and do the same thing by pulling open rows and data filter, right? And if they, let's say look at one standard deviation beyond the mean, so they can go through this whole process, they'll find that the probabilities aren't going to match the normal approximation, right? And that is sort of troubling for students at the first time. They're already expecting everything to look normal. And I love starting that way, then saying, well, start moving that sample size larger. Let's see what happens when we have each sample, each of the 10,000 samples we draw has a sample size of 10. Wow, so now this is starting to get a little more normal looking. We could actually plot the normal curve here so they can get a little assistance in seeing how normal it really is. Let me reset here, and let's say samples of size, let's do a samples of size 100. And now let's drag this axis out so we can see this clearly. That sampling distribution, the means themselves are approaching a distribution, that attractor distribution of the Gaussian or the normal. And so, empirically, they can see the consequences of the sample size and how that is affecting the distribution of sample means. And so I think that's a phenomenal way for students to do this. And so the sampling distribution demo here, this can take an entire class with students, and you can ping them. And I love to put them in groups because peer instruction is a really powerful way for students to not only gain agency over their own learning, because they're in groups and they're talking with each other. And usually within a group, someone will have some sense of how something works, maybe more than another. And so they're teaching each other, putting them in groups and giving them this sort of guided challenge, giving them a little bit of instruction on what to do, but then have them interpret and discuss. They leave that class, after one class of playing with sampling distributions with a much better understanding of what they actually mean than doing, 50 problems working through formulas on the standard error. That's not going to give them the depth of understanding that really working through something and working through the simulations will provide. So the sampling distribution of sample means is a great teaching module to start off with in that really core part of the course. And I'll mention that we don't just have it for the mean. So if you go back under the sample data, examples for teaching scripts, interactive teaching modules, there's the same sampling distribution, but for the sample proportion. And so if you start with proportions and not means, that's certainly something you can do there as well. All right, so beyond the sampling distributions, perhaps the next thing that is often very difficult for students to grasp without really seeing how it works is confidence intervals. And just like the sampling distribution demo, there are population characteristics along the left here, demo characteristics, and then how you want to run the simulation. And the basic structure of this is when I click Draw Sample, JMP will show the distribution of sample data from that population. So we had a sample size of 25 here. We drew one sample with a 95% confidence interval. And what we're looking at here, so the line in the middle is actually the mean that we have specified up at the top, so a mean of 0. So that's the population mu. And then we're looking at the confidence interval for each sample. So as I draw samples repeatedly, we're going to see the confidence intervals and whether they span the population parameter. Now you'll notice a few of them did not capture the population parameter of mu. That confidence interval here, which is red, and that one here, which is red, or that one here, which is red. And JMP's going to keep a running tally of this and show the proportion of confidence intervals over all the ones that have been drawn, in this case now 58, what proportion or percent of those have captured the true population mean. Now what this means is, let me draw 100 all at once. So if I click draw, out of the 100, we can see, well, 94% or 94 of them capture the population means. Students can kind of get an understanding of what does a 95% confidence mean. Certainly it doesn't mean that each confidence interval has some percent chance of covering mu. Of course, each confidence interval either does or does not. There's no probability once a sample has been drawn. It either does capture mu or it doesn't. But over the long run, right, that's what that confidence is really reflecting. And it's very easy to show, if we do 1,000 draws, well, we're going to get very close to 95%. Out of the 1,000 or 10,000 or 20,000 we draw, it's going to be somewhat different then, but no, it's pretty close. 95.18% include the population mean, right? That's a long run probability. Now, there's a couple additional things that can be done even beyond just the basic idea of how a confidence interval works. Remember, we can change the population shape. And if we change it to skewed right and have a small sample size, let's say sample sizes of 3. So if we have just worked through the sampling distribution demo and they notice that, when you have a skewed population, you don't have a perfectly normal sampling distribution of the mean when you have small sample sizes. Now, really advanced students can probably intuit through this, but you can actually give them the tools to play with this to see, well, will I have 95% of my samples capturing the true population mu when I actually have a population that's not normal? The confidence intervals are built using a normal approximation. So if I click draw here, well, 88.72% of them actually capture the population mean, right? Because we're not actually modeling probabilities correctly by assuming a normal sampling distribution when we have a skewed right population. Right? But again, that will certainly clean itself up when we have larger samples, right? The normal distribution comes into play because of the central limit theorem, and so it saves us a bit in our estimation of the confidence intervals. All right, so that's a great demonstration, and depending on how advanced you want to take your course, can be used to show a lot of different concepts. And so there's the one for the confidence interval of the mean, but also one for the confidence interval of the proportion. So depending on which you want to teach first or how you want to teach them, that's a great demonstration. Now there's also one for the hypothesis testing of the mean. And so like the demos before, population characteristics set up on the left, we can name the variables, give them a different mean and standard deviation. I'll again do 60 for the mean and 5 for the standard deviation. The demo characteristics have a couple of additional fields now. Since we're doing hypothesis testing, we have to specify a null hypothesis. So if the null hypothesis is 60 and the population mean is actually 60, well, the null is true. So every draw we're looking at is really under the condition that the null hypothesis is true. And we're going to see the t-statistic here. And so we'll see the proportion of rejected hypothesis tests. And certainly after teaching a little bit of hypothesis testing logic and how this works, we should see if we draw, let's say 1,000 samples at once, really only 5% of the time should we be rejecting the null hypothesis. By chance alone, we will, however, get samples that have t-statistics exceeding our criteria. Right? That's how sampling works. And we set the criterion as a function of really how unlike the samples under the null hypothesis do we need a sample to be before we're willing to think that the null hypothesis is no longer a good description of the population. And so this gives students a way to play with this concept empirically, and then to play with the concept of power empirically. So if the null hypothesis is actually that we expect means that are 59, right? So under the null hypothesis, let me draw 1,000 samples there. Notice the t-statistics on average tend to be a little more positive, right? Because our true population mean is actually one more than what we expected it to be. And so our t-statistics will tend to be more positive. And look, we're actually rejecting that null hypothesis more than 5% of the time, 13.8%. And this is no longer our empirical estimate of alpha. This is actually power. This is our 1 minus beta. And so this gives students a nice way to play with these concepts and to look at power empirically, and also giving students a sense of the fact that even if the null hypothesis is false, that doesn't mean a hypothesis test is guaranteed to reject the null. In fact, we know it's not, and they should know it's not. Now, again, depending on how complicated or in-depth you wish to make the course, starting with different population shapes, you can introduce students to how violations of test assumptions can affect certain things. So starting with a skewed right population, if we have a very small sample size, if the null is true, let's set it back to 60, we can ask students, what proportion of the time do we expect distributions, or do we expect our samples to be able to reject the null? And notice I actually had a t-statistic here of almost 150. So the null is true. We have a very small sample size, and my false alarm rate was 12.5%. Right? So a violation of that assumption of my test has a critical consequence for my false alarm rate. But that's certainly not the only consequence that a distributional violation can have. If the null hypothesis is false, that violation will also have consequences for my rejection rate. That is, consequences for power. And so my power dropped from about 12% previously to about 8.3%. So giving students a way to work through the sort of the dual consequences of violation of test assumptions. It's not just a problem for our false alarm rate, it's also a problem for power. And so having students really understand that concept works very well by working through this empirically. And again, this could be several class sessions working through just this demo. All right, so that's hypothesis testing for the population mean. Again, there's one for the population proportion. So depending on which you teach first or when you want to teach it, those are worth playing with. And then finally, one of my favorite teaching modules, and this is demonstrating linear regression. And this has a huge amount of functionality. And so I'm only going to show a little bit of it right now. But just so you get a sense of how it works, again, population characteristics are set up on the left. In this case, now we're setting up population sort of linear regression. So the intercept, slope, and correlation between the variables in the population. We can name our x and y if we like, and we can change the mean of x and the standard deviation of x. This all gives us nice ways to work through how, the standard deviation of the x variable, the spacing of the x's, sort of affects our ability to detect differences and all of that. But I want to show you just some basic ways that this demo works. So I'm going to expand this section here, the summary of all samples, and this black line is the population slope and intercept. That's the population linear regression. So if I move anything here, that'll change this one. And so I'll leave it exactly where it was before. Now, when I draw a sample, I want you to see what happens. I'll draw a few here. What JMP will do is plot each sample around that population line. And as you might expect, knowing what you do about linear regression, there's a point within this distribution, so the mean of x and mean of y, that's maximally stable. And all the points are really revolving around that. And what you get by drawing all these samples is you actually get an empirical working hotel and confidence band. The confidence band that students see when they actually fit a linear regression. Well, they can get an understanding of why that line is there. Given there is a true population relationship, every sample is just one instantiation or guess about where that line is. And as we move away from the mean of x, our prediction or our confidence with where that line is decreases. And so we get this nice envelope around the linear regression. Now the red triangle here, and again, if you're new to JMP, the red triangles are little menus that always let you do more things. Under here, you can actually turn on different things than just the population slope and the sample slopes. That is, we can actually look at the distribution of the intercepts. So what intercepts we estimated with each sample. We can look at the distribution of slopes. So this is the sampling distribution of the sample slopes. And I find this is incredibly powerful to show students because after they've worked through the distribution of sample mean, sometimes when they get to regression, they have this misunderstanding that when you get a sample slope, that is the population parameter. And of course it's not. Like all sample statistics, it experiences error. And so showing students that there is a distribution of sample slopes is actually really powerful. And once you show enough of them, let's draw 1,000 all at once. Of course, this distribution will look normal, right? This is a normally distributed sampling distribution, just like that original sampling distribution of the mean was, under a lot of conditions. Also under here, we can look at the correlations we get, the R-squares, the t-ratios, p-values for the intercept, and also p and t values for the slopes. So we can do a lot with the sampling aspect of this demo. And so certainly teaching inference from linear regression, this is a great demonstration for that. But that's not actually the reason I love this demonstration the most. And I'm going to drag out the scatter plot for you to see this. Under the red triangle for the sample data, we have a number of tools that let us investigate conceptually what is happening with linear regression and how does linear regression work. And the first thing I'm going to show you is something that's nice to do with students when they're first getting to know linear regression. That is, first getting to understand what it is to fit a line to data. And what I like to turn on is this fit my line. And what that gives them is this blue bar with handles. That's what the little dots are. And they can move this line around by grabbing the handles. And so one nice sort of exercise for students to do is to find the best fitting line themselves. That is, put the line where they think it should be. And you can look at your residuals on the right, which is a nice thing to do. And from here, you can actually have them compare the best line that they can come up with to the true line. So you can turn on the fit least squares line. And they can say, oh, I was a little bit off. They can see what the true line should have been. So let me turn off the fitless squares line. To make it a little easier for them, they can actually turn on their residuals. So if you click Fit My Residuals, that'll show for each point the deviation between their line and those points, which gives them a nice understanding of what a residual even is. So showing the residual here and mapping that onto the residual plot right there. They can also turn on their squares. And of course, when fitting a linear regression line, we're not concerned with the magnitude of the residuals themselves. We're concerned with this total magnitude of the squared residuals. And so showing the squares, the area of these squares is the contribution of each of those residuals, right? So each residual is not contributing its actual value, but the square of its actual value. And so when you do this, you also get the little sort of temperature gauge, like thermometer here, measurement of how much your sum of squares error is total. And so they can find the point that kind of minimizes that. And that's a great way for them to play around with this. So let me turn the show my squares off. Now, that's something we can do when first getting an understanding of really what the line is and how this works. But something else I think is really fantastic about this demo is if you fit that least squares line, so the one we turned on sort of allows students to compare their own line to their fitted line, this line actually reacts to where these points are. That is, if I grab a point and move it, this line will react in real time to where that point is, which actually opens the door to a large number of conceptual exercises we can do. And I'll just point out a couple of my favorites. Now, first is understanding how a point influences the fit for the line. And so putting a point right at the mean of x, so right here at 10, if I move a point up and down, having students understand or see that that point and points near the mean of x really can't exert any influence on the slope. And so no matter where I put this point near the mean of x, it's not going to affect the slope. And so you can see how much influence that has. Now, if I were to take a point far from the mean of x, let's just move it up along the line here, moving that point even a little bit influences the slope quite a bit. And so this gives students a great way of understanding why we are so concerned in linear regression about leverage points. That is, let me drag out the axis here, and let's just make a true leverage point. So, a point that's extremely far from the mean of x, moving this point even a little bit controls almost entirely the slope of the line, right? So that point, a single point in the data set, can exert a tremendous amount of leverage on that linear regression. And the great thing about linear regression is, and if I move it back to the middle, you can see how moving it does nothing. The great thing about linear regression is it's such a physical connection to the statistics. And in JMP, being able to move those points around like this, I think gives students a great intuitive or physical sort of connection to the statistical analysis. Now, of course, being able to work through the analysis on the right-hand side, understanding the intercept, the slope, and what those things actually mean, that can be added on after this point where they really understand how the regression line is reacting to the points within the data set. And I think that attaches to that understanding very well. And so I think giving students the ability just to play with the data like this is not only fun for them. My students always found it to be incredibly fun to play with the linear regression line like this, but it added to their understanding in a really substantive way. So under this red triangle, you see a number of additional options. Depending on how you like to teach linear regression, some of these are really useful. Fitting the mean to the data, so showing where the mean is, gives you the ability to talk about the sums of squares, sort of regression versus the sums of squares total, right? Putting on things like density ellipses, this shows you, it's a nice reflection of the correlation or the density. And so moving points around, of course, everything here reacts to that in real time. And so this is a great demonstration to play with, demonstrate linear regression, and a large number of things you can do with this. And so use your imagination and map it onto the ways you like to teach. And there's certainly something in here that can make those concepts come to life for your students. All right, so those are the teaching modules that are available under the Teaching Resources section. And there certainly were more. So under Sample Data again, look under the Teaching Scripts, Interactive Teaching Modules. And there were a few I didn't talk about yet. There's a Demonstrate ANOVA, so demonstrating analysis of variance. The Distribution Calculator I talked about only briefly. But the hypothesis testing for proportion, confidence interval for proportion, and sampling distribution proportion, we didn't talk about, since they're essentially the same as the means, but for the proportions. But what I want to talk about now is another section, these teaching demonstrations. And there's a large number of them on the left that we could talk about, but I want to talk about just a few of these, the ones that I think are appropriate, certainly for beginning statistics courses. And one I want to talk about, especially when you're first starting and getting into representations of data, are dot plots. And so I'm going to bring open just a basic data set here from before, that iris data set. And the dot plot, when you run, instead of making a histogram like JMP normally does, so under Analyze Distribution, if you get a histogram of, let's say, sepal length, right, that histogram, although interactive and wonderful and works like a real histogram would, it doesn't show individual points for each observation in the data set. So that first conceptual leap for a student, that an individual point is occupying just one part of a bar, although you can select in the data set and sort of show that, it's not as manifest as something like a dot plot can do. And so a dot plot, if you haven't seen it before, I'll make one for sepal length. So if I click on sepal length here, what it's doing is it's coloring the dots by species, so I can do that here. And so each one of these dots in the data set is one of the observations. And certainly here we can change some of the overlap, so we can make the vertical overlap more or less. We can change the dot width, so we can sort of restructure this to make it look cleaner or not. But the idea is that you want to make very manifest what these observations are. So the two I selected here, those two varus colors, right? Those are two observations in the actual data set, right there and right there. And the dot plot lets students really understand why a histogram is showing what it's showing. And I like using them in conjunction, actually. I like to sort of have both open at the same time. And when I click the, let's say, the 4.5 to 5 section, showing that those observations, those flowers, get binned together in a single part of this histogram. That's a nice way for students to make the final connection between the data in their data set and the representation of the data in the plot. So the dot plots is a really nice way of showing those things. And so certainly play with this. You can do a number of things, splitting by species. So if we want to split the axis and just show them in different bins here, that's also a nice way for students to look at the separation among those observations. And so that's the dot plot. Now, another thing you might be interested in showing, and this is certainly a modern way of demonstrating inference, are permutation tests or randomization tests. And so permutation testing, the idea here is to create a sampling distribution empirically from your own data. That is, presuming that you were to shuffle the labels, let's say, of species, and wanted to look at, let's say, differences in terms of sepal length. So if we wanted to, let's just compare two of these different flowers. If we were to potentially resample and actually create a difference score between the sepal lengths for these two different flowers, right? So if we were to resample and actually shuffle the group labels, so every time we did this, we shuffled which got to count as each of those flowers, we can create a distribution of differences that would allow us to look at how unlikely would it be to get the difference we observe. Now, permutation testing is actually made very obvious. The resampling demo is a pretty basic one, but it becomes very obvious if we use this randomization testing add-in that one of our colleagues at JMP actually created. And so if you go to the JMP user community, community.jmp.com, you can search for this randomization test add-in. And I'm just going to show this to you briefly, but this is a great additional tool if you do like teaching with randomization testing. And so I'll go down here, randomization testing. It's going to ask me to choose a data set, and I'll choose two unpaired groups here. And let's actually, I'll just go here actually and use analgesics. So this is a basic data set where we have measurements on, let's say, drug and gender, and we're looking at pain. So the observations in this data set are basically how much pain people report, and we're going to look at their sex here. And the way this starts off with is by showing us the original sample and the means of the two groups. So there's actually a difference in reported pain. Men are reporting more pain than women in this sample. So a difference of 3.5693 is the difference between those groups. But what would happen if we were to resample or permute the labels of our observations, that is, reassign whether people are male or female, then recalculate that difference, and we were to do that 1,000 times? And if we were to do that 1,000 times, we have a distribution centered at 0, because the null hypothesis is literally true if we're just reshuffling the labels. And each of these samples we can click on and actually see. So if I click on one of the samples here, right here towards a mean difference of 0, some of them were originally in the female group but now are called males, and some were originally male and called female. The difference was 0.211, so a very small difference between those groups, which we typically would expect if we're just reshuffling the labels. What we can see is that our original sample difference, the one we originally got with the real labelings, was pretty unlikely to happen by chance alone. And we can actually say, well, how unlikely was it? Give me a two-sided p-value. So we get an empirical p-value here of 0.004. And like everything in JMP, these are interactive, so we can grab the handles and look at what proportion of the time do we get a difference of 2 or more in either direction, or whichever sort of difference we want to look at. But the value of this add-in is that we get to look at the idea of inference from data from the perspective of simulation, or from the perspective of an empirical sampling distribution. And we can do the observations by resampling, by shuffling, by shifting. There's a lot of controls here that let you show these differences depending on how you want to teach this kind of simulation approach to inference. And so that's a great tool if you are teaching with randomization testing. The very simple version is that permutation test for two means or medians that's built in, but I really highly recommend downloading that randomization add-in if you like teaching with that sort of thing. Right, so those are a lot of tools in JMP for teaching statistical concepts. Now, the great thing about JMP in general, though, is that statistical concepts are pretty visible even when you're teaching statistical practice. And what I mean by this section is how do we teach actually how to carry out data analysis within JMP? Now, I will point out there are some calculators built into the software. These are, again, under Help, Sample Data, Teaching Resources. And what I mean by calculators, and let me show you just where they are, Sample Data. We're going to go under calculators here under teaching resources. What these are if you're teaching from summary statistics and you want a student to, let's say, calculate a hypothesis test for one mean, and they only have summary data. The value of these little calculators is they can put in their hypothesized values and their observed values, and it'll calculate, let's say, the z-test for them or the t-test for them. Now, this saves them from carrying out a lot of these by hand, but I'll tell you, my honest best way of doing this is certainly not teaching from the calculator standpoint. Have students carry out a few hypothesis tests by hand, maybe at the very beginning, but very quickly switch over to using real data. Just sort of like the Gaze guidelines point out, using authentic sort of experiences with data tend to lead to the best understanding of statistics. So while these are here, I certainly don't recommend them as the best way for students to really carry out analysis. Let them use the software and let them analyze data like a real data practitioner would. And in JMP, there's sort of very comprehensive analyses within JMP, but the main ones you'll use really in a basic statistics course are certainly summarizing and graphing. And this is not a webinar on how to use JMP. I'm going to point you to one in just a minute that is great for getting started. But just to give you the quick overview, graphing as JMP is made really easy and powerful using Graph Builder. So under the graph menu, where you can simply drag and drop variables to different sections and turn on the types of plots you're looking for. So box plots, bar charts. If I start off with two quantitative variables, we get the scatter plots with linear regression lines. We can drag on confidence ellipses, right? So graphing is very, very simple and straightforward in JMP. Tabulating is also similarly easy under Analyze, Tabulate. Sometimes we really just want to get a table of means, and we want, let's say, for different species, for the sepal length and sepal width, and I want the mean and standard deviation, right? I can simply drag these to create the table. And again, this is not a webinar on how to use JMP for these things, but notice that, even within JMP and its active analysis, things are meant to be easy and quick. There's even an option for now text and unstructured data. So I'll pull up in a different data set just to point this out. So if you have data like this, where you have, 1,900 observations for different flight failures, and we have the narrative for what happened, there's a platform in JMP now to process those narratives. So it's called Text Explore under Analyze, where we can put in the text column. It'll spit out right away a term and phrase list. So phrases that often occurred, terms that often occurred. From here we can get things like word clouds. People tend to like their centered word clouds, so I'll turn that on. And just like everything else in JMP, these are active. So I can select the rows where pilot was mentioned, or select the rows where failure was mentioned, and maybe we can investigate what's going on with these. So text analysis is now possible, even in a basic class. Now, for basic analysis, we typically cover a number of different things in an intro class: univariate hypothesis testing and understanding. So that's one variable type analyses, which is all done under the distribution platform. Now, one thing I'll mention about JMP is built to organize analyses based on their context. So when I say that distribution is all for univariate analysis, what I mean is when you go into the platform and cast a column into a roll. So when we started this off, all the univariate analyses we can do from this point live in this platform output. So under this red triangle, right, and JMP does this everywhere, the next step or the next analysis all lives here. And so if we have a quantitative column like sepal length, something that JMP would call continuously modeled, we can do things like test a mean. Maybe under the null hypothesis, I expect that mean to be 6. When I run that analysis, the output populates the same window. So there's our p-value, there's our test statistic, and we always get red triangles that let us do more things. From here, we can turn on a p-value animation, right? Even when we're performing a practical analysis, there's still tools in JMP that let us try to understand the consequence or sort of the interpretation of the output. And so the power animation is also nice here. So understanding the power given some specifications under the null hypothesis and the alternative. Right, so that's univariate analysis. For bivariate analysis, everything that counts as one variable predicting another variable all lives in one place as well. So this is analyze fit y by x. And so here, again, depending on the type of data we give JMP, because it's based on context, JMP knows what type of analysis to give us. So let's say we're predicting from species to predict petal length. When I click OK, JMP will give us a certain type of output. It's called a one-way. And under that red triangle are all the analyses that make sense given that structure of data. One categorical X predicting one continuous Y. So things like the means and ANOVA, things like comparing means with a Tukey or a student's t-test, or testing for unequal variances or equivalence testing, or even non-parametric tests. So if I turn on any one of these, they'll append to that output. And because JMP is contextually sensitive, if I go back to fit y by x, and let's say predict from something continuous, petal width, to sepal length, right? This is now a different context. Even though the output looks pretty similar, when I go to that red triangle, rather than giving me options for an ANOVA, it gives me options for things like a line, right? So fitting that line, and even more options under the red triangle, like that confidence interval for the line that I mentioned earlier, so giving students an understanding of the error and estimating the line. Right, so JMP is built within this contextual format. And actually, let me pause and just mention, pedagogically, this is incredibly valuable. The way I always like to teach was not about the particular analysis, but about the question they're trying to answer. And JMP worked really well with this structure, telling students, well, if you're understanding relationships between two variables, that's one place in JMP. And depending on the type of data you have, that's going to circumscribe the set of analyses that are appropriate. So if we're predicting species by petal width, right, not the other way around, that's a different type of analysis. Now we're talking about a logistic regression, in this case, an ordinal logistic. Right, so JMP will help students get to that right place and give them the type of analyses that make sense. And you can certainly understand why an engineer and scientist in the real world uses something like JMP, certainly because it's so quick to get to the right types of tests and get to the answer without having to pick from a large menu of different options. So once you get to more than two variables, and this happens in some introductory stats classes, there's a platform called Multivariate. Multivariate is all about understanding multiple variables at the same time. So under Multivariate Methods, Multivariate, and I'll just show you rather quickly here. The idea here is to look at certainly the scatter plots and the correlations, and this is also where you can get into things like principal components, outlier analysis in multivariate space, or even ellipsoid plots, and so students love these ones. 3D is not always the best way to understand data, but it certainly makes for a pretty visual, and sometimes actually gives some nice sort of meaning from your data, especially when looking for outliers. So that's multivariate methods. And finally, fit model. So when you're looking at a modeling a system with more than two variables, fit model is where you would go. So if you're, let's say, fitting a multiple regression, one variable predicted by two others, plus potentially, let's say, the interaction between the two. So I'll pick one on one side, one on the other, hit cross. Right, so now we can run this multiple regression. And again, everything in JMP, there's always some way to visualize or understand these variables in a more complete way. And so under the red triangle in fit model, always go to factor profiling and turn on the profiler, because the profiler is a great way of understanding this relationship. What you're really looking at is the predicted y-score plus a confidence interval based on the values you put in for each of the input variables. And because our model had an interaction, notice that the slope on the left-hand side changes when I'm at different levels of petal length. Similarly, the slope on the right-hand side will change at different levels of sepal width. Right, so that's reflecting the interaction in the model here. And so JMP always gives you more ways to understand what's going on. And so even the surface profiler here, a great way of understanding multiple regression when teaching it. So JMP has a lot of depth when it comes to teaching statistical practice. But one nice thing is to teach these methods in JMP, and this is critically important when you're first getting started teaching. You don't want to be teaching students how to carry out each analysis. Certainly, you want them to know how to do it, and you want to give them support. But if you go to our jmp.com/academic page, under the Learning Library, there's a great set of resources to off-put a little of the burden of teaching how to do each of those analyses. And in the Learning Library, which you can actually get to directly by going to jump.com/learn. For each of about 85 analyses, we have videos and guides. So for instance, let's say you wanted to teach them how to do that simple linear regression. So I'll go to the correlation and regression section. And under here, simple linear regression is a section, and you can click and watch a 2 to 5 minute video. In this video, it's going to be 2 minutes and 30 seconds, so directly on how to do it. Or, and these are great to include in your syllabus, a 1-page guide. So this is a single-page PDF using sample data, so under the sample data library, and it gives them step-by-step instructions on how to carry out that analysis. So no matter what book you teach with, or no book at all, these allow you to give students all the details on how to use JMP for these particular analyses. So again, remember that website, jump.com/learn, or find us again at jump.com/academic and navigate to the learning library. And actually, while we're on that topic, let me go back here to the jump.com academic. We have case studies and certainly other course materials that you can use to teach those same concepts. So if you're teaching regression, one thing I really love, let me go to course material library. So under here, you can actually look under these different courses, and one that I think is really handy. So if you look under, let's say, regression modeling and analysis, the 1-page guides are all listed here, and the case studies that are all useful for regression analysis are all listed. And so that's a great way to find some case studies and guides that are really useful. Now, if you know you're using case studies specifically, go to the case study library section, and under here you can even browse by type of analysis. So if you're looking for, a case study, so real data that has a real question, and you're trying to teach, let's say, descriptive or exploratory analyses, you can check out these case studies. They all come with sample data, or come with real data, I should say, and a context that allows students to really understand why they're analyzing. All right, so just a couple of quick things before we take some questions. For testing and evaluation, there's a JMP for Grading and Assessment webinar where I talk a lot about how you might grade and assess students with JMP and how you might create really example data sets or data sets for tests. JMP also integrates with WebAssign. So if you have WebAssign on your campus, there are JMP questions that are integratable. And so these talk about concepts and they use some of the JMP interactive output. Now, for in-class use, I'll just mention again, use a journal. Journals can be, embedded with data sets like I did here, with outline items, all sorts of things. And you can give them to your students before you actually teach the class so they can follow along. Also, use data table scripts. So when you run an analysis in JMP, you can save that analysis to the data table. And that's what the left-hand side is over here. To save an analysis, just go to the red triangle, save script, and save it to the data table. Now, the value for this is if you save the analyses you're going to want to talk about during a lecture, if students can't keep up by going to the menus quick enough, you can tell them, oh, just click the play button next to Scatterplot 3D, and they can have it on their own computer without having to go through the menus. Now, as far as students getting JMP, again, go to our academic page, and there's a whole section on getting JMP. Academic licensing is really easy. Most schools, most universities have a license, so students should be able to get it basically for free if the school is giving it away for that much. There's also at onthehub.com/JMP student licenses, so students can get it for 6 months for $29. So for less than a cup of coffee a month, they can get JMP, so professional statistical software that they can put on their resumes. So definitely worthwhile for students. Finally, some resources to remember, jump.com/academic, and that'll take you to the main academic landing page. And remember to look under the help section, help, sample data, teaching resources.